This conference will now be recorded.
Okay, so welcome everyone. Today we have Patrizia. She's going to talk about this, recent. I think it's going for a while. This debate about leap second, should we add it or not, and what's the benefits? What's the headache we get from it? So, with no further ado, Patrizia, how about you introduce yourself, and we'll get started from there.
Yeah, Ahmad, please, how much time do I have?
You have 45 minutes. I mean, you can have a lot, a part of it for questions and so on, and we can continue from there.
Okay, fine. So I try to share my screen.
Yes. So let's make you presenter. Make presenter. Here you go. You should have the permission now. Is it working on your end?
Yeah, it's coming.
Perfect.
So do you see my screen?
Yes.
Perfect. Okay. So thank you very much for inviting me. I am from the International Office of Weight and Measures in Paris, and our aim is to maintain measurement standard for all the world. And particularly, I am in charge of the international time reference, and I'm happy to discuss with you the issue related to the leap second, because we are very much engaged and committed to work on this topic, and I will be really happy to have your feedback. Just to tell you something, this international organization was born in 1875 when the Demeter Convention was signed, where after the French Revolution, it was considered very important that all the meters were meters and all the kilograms were kilograms. So the international organization was created with the headquarters in Paris. And you see that we have several governing bodies. I would like to draw your attention on the General Conference of Weight of Measurements, because I will talk about that. This is where all the member states take decision, and they meet every 4 years, and next time is November 2022. Then we have a technical committee, and the one which concerns time and frequency is called Consultative Committee on Time and Frequency. And this is where we are in Sèvres, close to Paris. Our aim is to represent the measurement community, to be a center for scientific and technical collaboration, and to coordinate the worldwide measurement system. And we also take care of capacity building and knowledge transfer. Let's go to the time methodology. I think I'm telling you things that you know, so I didn't know which was the expected level, so I am quite general. If you have any question, I will be happy to go more deeper. So from 1967, time is given by atomic clock, while before it was the rotating Earth which was giving the time standard and on which we set the clock. The first definition of time scale and time measurement unit is based on the rotation of the Earth on the day, because the alternation of day and night is very natural, very observable. It was known that there are some change during the year, but the mean solar day was deemed constant. And so the solar day was divided in 24 hours, 60 minutes, and 60 seconds to obtain the second. And the Greenwich reference meridian was chosen. And in 1925, astronomers who were in charge of timekeeping decided that it was better to call the time related to the rotation of the Earth universal time, because at the beginning the day started at noon and finished at noon. So they changed with a day starting at midnight. So they asked to call this new time scale, timekeeping standard, the universal time. This was based on the idea that the rotation of the Earth was constant. But actually, around 1850, something was not clear, because looking to the polar star, which in the northern hemisphere should be exactly on the rotational axis of the Earth, this star seemed to be moving. And it was actually the rotational axis of the Earth which was moving, with a random movement that can be observed but not predicted. And if you think to the intersection of the rotational axis with the geoid, this is the point which you see is moving, and it can move about 10 meters very slowly in the century. This type of movement is monitored by the International Earth Rotation and Reference System Service, which is in charge to measure all the data, all the movement of the Earth. There was another variation which was quite important. It was observed, look around just before the Second World War, that in summer we spin faster. A simple explanation, not very rigorous, but please allow me to give a simple explanation. If you see a dancer, when she spins with open arms, she has a certain velocity. When she closes the arm, she spins faster for the conservation of momentum. If you think on the Earth, in the northern hemisphere, we have many mountains. In winter, they are covered by snow, so a lot of mass is far from the rotational axis. When in spring the snow melts and the water comes down closer to the rotational axis, we spin faster. As I told you, it's not very precise, but this gives an idea of what happens to the Earth rotation. And the most important effect is that for friction, the Earth is slowing down. So if you look to the last thousands of years, you see that the duration of the day is getting longer. The time for the Earth to accomplish a complete spin is getting longer. It is about 1 millisecond each year. So it was clear that the rotation of the Earth was not the best standard. It was corrected by polar motion. It was corrected by seasonal variation, but it was never precise enough. And when the technology was mature enough to be able to measure the irregularities in the Earth rotation, it was decided to change the definition. And the definition changed in 1960, even if the atomic clock were already available, was based on another astronomical movement. It was deemed that the revolution of the Earth around the Sun was constant. So it was a bit complex to measure how long is 1 year and divide the year in fraction, this number of fraction, to obtain 1 second. But with a lot of effort from astronomical observatories, this was done. And have a look that it was not said that the second is this fraction of any year, but the second was this fraction of the year 1900. 1 year was chosen as a standard, and this was done with many measurements. But consider that they were in 1960 and they have chosen 1900 as reference duration. And as any time you change the definition, you have to assure that the new definition is equivalent to the previous one within the uncertainty. This ephemeris second was in agreement with the universal second in the year 1900. But in the year 1960, the universal second, the second based on the rotation of the Earth, was already a little bit longer with respect to the reference 1900, which was chosen to define the ephemeris time. The ephemeris time had a very short life. In 1967, the definition of the second was changed again. As you know, in meteorology, we are very, very prudent. We are not changing our mind very quickly. So this change in definition in 7 years is really a record, because the ephemeris second was so complex that in the end it was abandoned. And atomic clocks were available. So it was measured. How long is the period of the radiation coming out from a certain special good atom, which was cesium? How many cycles of this electromagnetic radiation I have to count to get 1 second? And the answer is 9,192,631,770. How this number was determined? At that epoch, people knew the duration of the ephemeris seconds, and they made the measurements of the cesium radiation to count how many cycles were necessary to reproduce the ephemeris seconds. And you remember that the ephemeris seconds was already a little bit shorter with respect to the second obtained by the rotation of the Earth in that period. So everything is coherent in the year 1900. But when the atomic time was defined and the atomic second was defined, it was a little bit shorter than the fraction of the rotational day in that epoch. They were in agreement in 1900, but not in 1967. So this is why, by definition, the atomic second is a little bit shorter than the rotational second. And in addition, as the Earth is slowing down, we will never be able to have an atomic time, let's say, that is perfectly ticking. We'll never be in agreement with the Earth, which has so many irregularities, and particularly this secular slowing down, which is making the rotational day always a bit longer. So a compromise was deemed necessary. We are talking of 1965, 1970. Some users needed to have a civil time connected to the rotation of the Earth, because they wanted to know which was the position of the Earth with respect to the star and the celestial body. So it was decided that a compromise time scale was defined, UTC, the Coordinated Universal Time, which is ticking like the atomic clock, whose time scale is named International Atomic Time. It is ticking with atomic clock, but when this atomic clock reaches about 1 second of difference with respect to the Earth rotation, an additional second is added to wait for the Earth to be in pace with the Earth. We did that 37 times till the 70s when it was defined. And so today we have a difference between the atomic time and UTC of 37 seconds. And any time the Earth is late almost 1 second, a new leap second is introduced. I interrupt for a moment the discussion on the leap second because I thought useful to tell you something on how we compute UTC and which is the work at the BIPM. And then I will come back on the leap second. So this is the International Office of Weight and Measurements, the Bureau International des Poids et Mesures. where we collect the data of all the atomic clocks which are maintained in national timing laboratory all over the world. So the second is defined based on the cesium atom. There are commercial clocks based on cesium or on other atoms which can provide an electromagnetic signal very precise. There are other type of, let's say, clocks, but they are actually something more. They are primary frequency standard, which are able to deliver a radiation which is extremely precise, more precise than the commercial clock. But the difference is that the commercial clock is continuously running, accumulating seconds and minutes and hours, while this device can work for some hours, for some days, in some cases for a month, but they are not continuously integrating second. And you see they have an accuracy which is in relative value 10 to the minus 16, which means they can accumulate an error of 3 nanoseconds every year. And the research now is such that new type of frequency standard based on optical transition are available. They are 10 to the minus 18 accuracy, so you see 100 times better. So the question is, should we maintain the definition of the second based on the cesium, or should we change? The Consultative Committee for Time and Frequency, the maximum technical committee devoted to time and frequency methodology, is working to change the definition in the next year. So we have clocks spread all over the world. We need to compute UTC. We compute UTC a posteriori. We are not working in real time. Real time is the job of national laboratories which have clocks and deliver services disseminating UTC, disseminating an approximation that we call UTC-K, where K is the name of the laboratory. We work a posteriori. We collect the data of about 450 atomic clocks, which are maintained in different laboratories all over the world, and they are about 80 laboratories. The clocks need to be compared, because if we want to know what time it is, we have the time given by different clocks. We need to compare them and to build a standard clock, a standard time. So we use mostly GNSS to compare clock. We have one clock in one laboratory, which is measured with respect to the clock on board to the satellite. In the same moment, another laboratory is measuring its clock with respect to the same satellite clock. We make the difference, and we can obtain the difference between the two ground clock without moving them from their laboratory. The GNSS is the most used system, which has an accuracy of a few nanoseconds. Progress are going on to use also other GNSS measurements and more precise algorithms. There are other techniques which are not only receiving but also transmitting to the satellite. They are called two-way satellite time and frequency transfer with a better accuracy. And the most promising techniques is based on optical fiber and optical signal traveling on the fiber, which can be even more accurate, but clearly not so easy to be used as a satellite time transfer. So with the measurements of the clock and their comparison, we compute something that we can say is a sort of weighted average. It's something more complex, but let's say we have different clocks, we measure their reading, and we make a weighted average. And we call in French échelle atomique libre, free atomic time, this weighted average. Then we have about 10 of those special frequency standards that I told you are much more precise, and we use them as reference to calibrate the other 450 commercial clocks that are less accurate. So we are able to see if there is any bias, any offset in the frequency, and we can correct the ensemble time, and we obtain the International Atomic Time, TAI. Then we have, then we receive the data from the International Earth Rotation Service. We know if a leap second is to be applied, and we obtain UTC, which is exactly the International Atomic Time, but the labeling of second is different. And the result of this computation is the difference between the real-time time scale generated by the laboratory and the international UTC. What we publish is the difference between the international UTC and the real-time approximation of the 80s laboratory. We publish something which is called circular T every month. So you can see, for example, in January, we published the data of December. We have one value every 5 days. These are the 80s laboratory. So the first laboratory is from La Plata in Argentina. And you see that in November, they had an offset of 258 nanosecond and so on. Other laboratory have a very small offset. And you can see in this plot, the best laboratory in the world can stay within 10, 15 nanosecond with respect to UTC. Remember, they work in real time. They realize their time scale in real time, and only a posteriori they can know what happened 1 month before. We have also a rapid solution, which is weekly. It is called Rapid UTC, and the results are available on the web. So this is to tell you what we do. Let's come back to the discontinuities on universal time. I think the first idea that leap second were a problem was published in 1999. Where the navigation system started to be a reality, the GPS started to work, and it was quite a problem for the manager of this satellite constellation to add a second in a certain moment on all the constellation. It was deemed a bit dangerous. So the GPS decided to, the GPS system decided to synchronize the GPS time and all the GPS clock with UTC at this epoch, 1980, when the GPS was born. But after that, GPS did not add any additional leap second. So in this moment, the GPS time is ahead 18 seconds with respect to UTC, because we have added here 18 additional leap seconds. The European system Galileo decided to put the same label on the number of seconds as GPS time. So Galileo and GPS clock are in agreement. The Russian GLONASS time decided to follow international standards and to apply leap second. So GLONASS time is in agreement with UTC, while the Chinese Beidou system, which was born more recently, synchronized its clock with UTC at a certain moment and then did not add the additional 4 seconds that have been added in recent years. So have a look if you have a smartphone and you want to know what time it is. You can find the option, do you want GPS time or do you want UTC or do you want Beidou time? And you have differences of seconds. And if you are educated and if you know everything, this is fine. But this can create a certain confusion. And what really pushed us much more is what you do and what I would be happy to hear from you. We know that digital networks have problem with the leap second because usually the computer don't have the second 60, so a minute which lasts 61 seconds is not easy to be introduced. this consultative committee on time and frequency had a survey last year, and we got more than 200 answers, and the large majority asked to eliminate the discontinuities. And what is also very important is that many users said we use GPS time or the International Atomic Time instead of UTC. And this is a problem for us because we want to have only one time scale and not so many with anyone using a different time scale with the risk of incident due to the bad synchronization. And I think you know better than me, this is related to the fact that in computers you count the number of seconds since a certain origin, and so it is not easy to add one additional second. And this is a problem particularly in Eastern zone, because we add the leap second at midnight UTC, which is 8 in the morning in China, 9 in the morning in Japan, where the stock market opens, and for them it is really a serious danger of problem. So what happened? Someone as navigation system decided to synchronize at a certain moment and then stop adding leap second. And so they have now another time, they give you another time different by seconds with respect to UTC. Other solution stops the clock on the second 59 and give the name 59 twice to 2 seconds. This happens, for example, on NTP, and this gives an ambiguity on 2 seconds. Other solutions like Google, Microsoft, Facebook, Alibaba decided to steer the frequency of the clock. Instead of having an abrupt jump of 1 second, they decided to slowly change the frequency so that in a certain period, 24 hours, 18 hours, this second is accumulated. So you see that these solutions are not in agreement, disagree with each other, and the users very often cannot tell which time is used by his source of synchronization. So what happens is that we understand that UTC in this moment is not satisfying many applications, that several methods have been implemented not universally and not compatible. This is a risk for UTC to become less relevant, but serious risk of incident are in front of us for these discontinuities and for the fact that there are multiple time scale. And also have a look to the last measurements of the International Earth Rotational Service. This is the difference between the rotation of the Earth and UTC. And when this difference goes close to -1, a leap second is added, and then little by little the offset is again accumulated. And normally this offset increase till we apply another leap second. But in the last years, the Earth has accelerated, and so the Earth has not accumulated any additional delay. Even some anticipation is now observed. So it is not very likely, but we could have a negative leap second for the first time, which has never been tested, and this could be even more dangerous than the other. So which is the solution? From the technical point of view, what we think is that we should say that UT1, the rotation of the Earth, should not stay within 1 second with respect to UTC. We could extend the tolerance we have to 100 seconds or maybe 1 hour. If we just put 100 seconds for more than 1 century, we know that there will be no discontinuities. If we extend this tolerance, in any case, UTC remains linked to the Earth rotational angle, and the origin is always Greenwich. And UTC will be an approximation of the Earth rotational angle, changing 1 second each year maybe, but well within the 15 minutes of seasonal variation that we have for the rotation of the Earth. So this is something that will not be visible. Before the Earth is late 1 minute, we need 1 century. Before the Earth is late 1 hour, we need 5,000 years. So it is not really a problem for the general public. But if we do that, UTC will remain a unique time reference under the authority of the General Conference of Weight and Measures, so under the authority of meteorologists, and UTC will be able to support the correct functioning of high technology system and the modern digital transformation. For sure, who needs to know the rotation of the Earth UT1 can find precise information on the IERS and NASA website. Global Navigation Satellite System with some update will still disseminate this value. Some radio station maybe will or not, but nowadays the most used time dissemination techniques is GNSS. And astronomers will need to update their software, but astronomers are an educated community and we rely on their capacity to do that without problem. So this is why at the General Conference of Weight and Measures this November, we have proposed a resolution which is called On the Use and Future Development of UTC, which asks to recommend the extension of the tolerance UT1 minus UTC starting from 2035. This year is a big discussion. Someone wants tomorrow, someone else needs time to update the equipment. So this date is still under discussion. But what is important is that we agree that the tolerance needs to be extended. And a new value will be fixed at the next general conference. Let's first decide that we do something and when. And then at the next general conference, we will fix which is the new tolerance and which is the procedures to apply when the new tolerance is reached. And we also think it will be good to revise this limit maybe every 10, 12 years to be sure that it was a good choice. Considering, as I said, that 60 seconds or 1 hour means 100 here, 100 or 5,000 years. So we are taking a decision for something very far in the future. This resolution has been published. Now the member states of the BIPM are discussing. They will meet in November and we hope they will approve this resolution. Also, the International Telecommunication Union is involved in this decision because in the 70s, the practice of inserting leap second was introduced in the committee of the International Telecommunication Union because timing experts met there to decide which was the code for transmitting time. So with ITU, we have created several committees. We have discussed so much. Maybe you have been involved. Unfortunately, it takes a lot of time. In this moment, we are highly committed to work together. We will have our general conference in 2022, and the International Telecommunication Union has a World Radio Conference next year. So it seems the good moment to take a decision. Also, other organizations, for example, the International Union of Radio Science, has sent an official position asking for a unique and continuous reference time scale, and they also asked to withdraw the present limitation on the maximum magnitude of UT1 minus UTC. Also, telecommunication, which is again ITU, but not radio communication, which is the one who deals with leap second. Those are telecommunication, the wired telecommunication. And they said in this document, continuous time without leap second traceable to a common time reference is what they need. And you see they are using GPS time because UTC is impacted by leap second. So we have several international organizations taking an official position. And so this is why this resolution that, as I told you, it will be discussed in November. So these are the exact wording of the resolution, recognizing that UTC shall be a continuous time scale, decide to extend the value by or before 2035. So hoping to have been clear, my message to you is help us to support this proposal. Please take any initiative to inform that this is the good moment to do something after more than 20 years of discussion, and help us with your point of view, with your needs, to be able to provide a reference time scale which meets your needs. Thank you for your attention.
Thank you, Patrizia. So let's have some questions. Anyone? Any question? So I have a question, Patrizia. Like we've seen some changes, like in, let's say, this last years, where we probably need to add now a negative second. Is that correct? Like, can you elaborate a
Yes.
little bit on that?
Yes, the fact is that, as you can see in this plot here, these are, this is a way of counting days. So this is the last leap second, which was applied in 2016, when the difference between the rotation of the Earth and UTC was going towards minus 500 milliseconds. So it was decided to apply a leap second to wait for the Earth, and so the difference went to a positive value. What usually happens is that this difference then increases again because the Earth slows down till it reaches again a negative value, and we decide to add another leap second. In these last years, this is about 3 years, from here to here it is about 4 years, the Earth has accelerated. So not only is not more accumulating delay with respect to UTC, but it seems it is anticipating a little bit. So if this behavior should continue, the Earth could be rotating as fast, let's say, as the ticking of the atomic time. We would not need any leap second, or even if the Earth should go faster, we should have a negative leap second to be able to remain in pace within the tolerance of 1 second. Yes, you understood correctly.
So is this also studied? I think it looks like there is a short-term behavior and there's a long-term behavior, right? So
yes.
So the short term we've been doing, let's say from the 1970, from what I'm understanding, is it's accounting for about a millisecond per day. This is what it looks like. But the long term is definitely not that, right? Is that correct, Patricia?
It is an integration. It is 1 millisecond each year. So the second year is 2 milliseconds and then 3 and so on. So this is why you see this slope. It is almost 1 second every year when everything it is regular. But there are many irregularities in the Earth rotation. And if you connect to this website, you can see that this difference, we can see maybe here, there are many other differences. There are periodical cycle, long-term cycle, and you see, for example, on the very long term, the Earth is slowing down, but sometimes it's going faster, sometimes it's going slower, and there are if you zoom, there are many different irregularities that are observed.
What is this Besselian year? Like, what is that? Is that?
Let's say year. This is the astronomical way to count the year, but we are in the year 2000. If we go back to before Christ, this was the duration of the day. The Earth was spinning faster, and so the day was shorter with respect to the duration of the day nowadays.
Okay. Is it a projection, or we have a way that we can see that?
This is based on the availability of measurements. You know, astronomers were working also before Christ and trying to put together all the measurements available. This is something which is based on real observation.
Interesting. Any other question?
It seems I have scared everyone.
I'm just curious, in the data center, do data centers use different times? I think she mentioned something about Tencent or Alibaba using one time, but in the US, do we know, or can we say most people follow GPS, most people follow UTC?
Yeah. In fact, in US, let's say, in US, most of the people use GPS time, which is now 18 seconds ahead of UTC, but this solution is not the same for everyone. If your time comes from Google, in the day of the leap second, they are not applying a leap second like an entire second, but they change a little bit the time, little by little, to obtain 1 second in 24 hours. And Facebook is doing the same over 18 hours. So there is a day, the day in which we add the leap second, in which different time are used, because the Google time Google time does not exist. But if you get your time through a Google service, you will see that the clocks is not changing by 1 second, but it is changing little by little. At the end of the day, 1 second will be accumulated. So the time you get from Google will be in agreement with UTC, but for 24 hours, they will not be in agreement. And Alibaba decided to do something similar. They steer, again, they correct the leap second over 24 hours, but 12 hours before and 12 hours after the leap second. So Google is anticipating the leap second over 24 hours. Alibaba is doing that 12 hours before and 12 hours later. So you see that there is a period of about 2 days in which we don't know what time it is, because if you follow UTC, you add a second. If you take times from Google or Facebook or Alibaba, you add a small fraction of second, which is different. And this is why we think that this confusion can create serious problem.
So we need basically a standard way to do the clock smearing, right?
I would prefer you do not do the clock smearing.
Of course, but it's good to have that as well, and let's say, and preferably not do it. But then let's say for systems that they still require it, we probably need a standardized way to do clock smearing.
Yeah, in this moment, I understand what the international standardization asks is to apply a leap second. So a second 60 at midnight UTC. I understand this is not feasible for all the applications. So I understand that you have to do something. I will never recommend that you reach an international standardization on the smearing. I would recommend that we stop the leap second. So you can use UTC and you don't need to take care of something which is an issue for you. And I forgot to say that the leap second was inserted because in the 70s, it was necessary to have the UTC, the civil time, in agreement with the rotation of the Earth. This was mostly for navigation because people used the traditional system for navigation and they needed to know which was the position of the Earth. But nowadays, almost no one is using traditional system for positioning. Everybody uses GNSS. And it is exactly from GNSS that we have this problem that dealing with a leap second is not easy. So I think that we should take into account that times have changed, and it is now time to give a service to the world for us, give a UTC reference time useful and adapt to the different application. So it would be more useful for me if you complained a lot saying that the leap second do not allow you to work safely and efficiently, because as much pressure as I have, as much pressure as we get, the easiest could be to take a decision.
Do you think it will be better, let's say, to stop where we are at the 37 seconds, or let's say push back, like go back to zero with like what do you think is like the best?
I think the best is staying where we are, because if we start adding a correction of 37 seconds, it will be maybe a problem. So why? We can survive with that. The important is that we do not touch anything, at least for one additional century, or maybe for 5,000 additional years, where if the Earth will be really 1 hour late with respect to atomic time in 5,000 years, if that would be a problem. I don't know which tanks I should use. If that will be a problem, maybe we will just change time zone and we will get 1 hour of difference.
Yeah.
Not a question, but just big thank you from me personally for like working on eliminating this madness, because every time we receive emails saying there will be no leap second added, we're like, yay! There will be half a year without outages and problems and whatnot. So yeah, thanks for trying to eliminate this madness.
Yeah, I completely share your point. The same is for me, because don't believe that it is easy also for our community. We are trained, we are used, we know how to do. But every January 1st morning, we check everything and we find sometimes problem. So it is completely clear to me. So if I can say anytime you have a meeting or anytime you have a journal or whatever, if you can write it down also on a web page, and if you can send me this written paper or text or page or whatever, this will be very useful, because in this moment we are collecting all the feedback and all the information we can from the users. And at the general conference in November, we will present a white paper with all the collected information. And so any additional piece of information is very important for us.
Patrizia, would you mind sharing your email? Like you have it somewhere, right? Because I have some of the audience that want to reach out to you directly.
Yes. So let me do that here.
Can we use the mailing list to share the link, like OCP mailing list, something like that?
Yeah, for sure.
Okay, cool.
But let's have the email also if anyone wants to directly reach out to you. Okay, so this is the email.
This is my email. I think you can see it. And please take the opportunity to talk of that. Take the opportunity to say that in November, the meteorology world, the general weight and measurements organization can take a decision, and it will be very good if the member states, United States is one of the member states, vote in favor of this proposal.
Yeah. Son, would you like to add any comment about the thing with Microsoft? If Son has the microphone. Okay, no problem. Yes, just like it was in the comments, like Son was saying that this Microsoft uses a smear at 1 second before leap second, and then they have a paper about it.
This is interesting. So, Son, may I ask you to send me a document which explain that? Because that I have never heard, and it is a very interesting information. I see the Ion PTTI 2019. Okay, I will be happy to have a link.
Perfect. Okay, any more questions? Okay, if no more questions, we can give you back 5 minutes then. Okay, Michael. Michael is here. Okay. Okay, thank you for everyone. Thank you, Patrizia, again for a very interesting talk. I really enjoyed it.
Okay, thank you, and hope to have some news from you all.
Perfect.
Bye.
Okay, bye everyone.